Hello, George Romanic here. In today's video we are going to talk about electrical conductivity of gases, and I will explain it using kinetic theory of gases. However, before we go into this rigorous mathematical derivation, let's first discuss this amazing device in front of me known as Tesla ball or plasma ball. As you can see now, it is set up to react to sound, but I will first turn it off completely because I would like to describe the basic parts of this device, and then I will turn it on and I will explain how it works when the power is supplied. You see, this device has two spheres. There is the outer glass sphere that keeps a mixture of noble gases inside, and these noble gases are mostly neon with a little bit of krypton, xenon, and maybe some other noble gases, helium. And there is inner sphere, this black smaller sphere, and electrical current is fed through that sphere. It's high voltage, high frequency current. Voltage is usually 2 to 5 kilovolts and frequency about 35 kilohertz. That means alternating current of 35 kilohertz changes direction 35,000 times in a second. So that's amazing. The device works by plugging it in a regular current. In Canada that would be 120 volts, in Europe 220 volts. And then what is happening is the following. You see, this mixture of noble gases is really poor conductor of electricity. We would say it's insulator. However, when we apply this high frequency, high voltage current to the inner sphere, it ionizes this gas and makes it plasma. What is plasma? Well, we say it's the fourth state of matter. We have gases, liquids, solids. And then there is fourth state of matter known as plasma. You see, I still didn't start my playlist on electricity and magnetism, but I can explain plasma in just few sentences. Atoms are made up of positively charged core or nucleus, where you have protons and neutrons. Protons are positively charged, neutrons do not carry electrical charge. And around nucleus you have electrons orbiting. And these electrons are negatively charged, and the whole atom is neutral. And electrons like to be connected to protons. They like to orbit protons because they are in the lower energy state compared to when they are roaming free. So to take electrons from an atom, you have to supply energy. And in this case, that energy is supplied by this high frequency current that is creating electric field. This electric field is strong enough to ionize these atoms of noble gases. Ionize means the positive core is left without negative charged electrons, and then you have positive ions and you have negative electrons that can conduct electricity, conduct current, which is happening here. So the question is also then, why is it glowing? Well, I just told you, you need energy to take electron from the atom, to ionize atom. Well, these electrons that are roaming around get recaptured by some positive ions, and they return that energy that was necessary to remove them from an atom. So when they return that energy, we see that as a glow. That's why these particular gases are inside of this glass sphere. I can convince you beyond any doubt that there is electrical field, and rather strong electrical field, around this device. And that's the following way. I have here a neon light bulb that is not ignited. However, when I put it here, look, I just turned it on. How does that work? Well, it works in the following way. The physics doesn't care if you have noble gases inside of this glass dome, or if you have noble gases here. As long as there is strong enough electric field to ionize these noble gases, you will have the same effect. As famously Richard Feynman said, same equations give same solutions. So you have the same effect inside of this device known as plasma ball, as well as inside of this light bulb. And isn't that just beautiful? I can also demonstrate to you that my body is much better conductor of electricity than the air. As we will learn later in this on this channel, air is very poor conductor. Look, when I put finger here, I am the one that is conducting electricity much better than the surrounding air. I am grounded, and you can see that the concentration of electric field lines is much larger at the tip of my finger than anywhere else in this free air, free atmosphere. Why is that the case? You have to study electricity and magnetism. It's called electrical induction. You see, this inner sphere is either positively or negatively charged. To be honest, I don't know. But the moment I put my finger here, it gets opposite charge compared to whatever is the charge on the sphere. And because my finger is much better conductor than the surrounding air, you have much stronger concentration of electric field on the tip of my finger. I am conducting that electricity to the ground and so on. You can see that, for example, wood is not so good conductor. When I touch wooden handle, it doesn't conduct so good. However, if I touch here metal, then I get much better results. You see, hammer can be used for many things, demonstrating these concepts as well. Particularly interesting is, you see this part of the hammer that has very sharp spike. If I put my finger here and I touch the plasma ball, I get electrified. I hope you can see it. And I can... Oh, this is painful. And I can smell it, because that's the burning of my skin. Now the question for you that I will not answer here is, why is it if I put my finger here on the flat surface, I don't get electrified, but if I put my finger on the spike, I get electrified? Think about it. And if you answer that question properly, please let me know in the comment section below, because that will also mean you properly understand why lightning hits sharp, tall objects. Now, before we go into mathematical derivations of electrical conductivity of gases, I would like to ask you to share this video with several enemies, perhaps even friends. Some of you might be asking yourselves, so what is the purpose of whiskey in relation to this experiment? There is no physical purpose, I just love whiskey. And it makes these discussions so much better. I have another actually question for you. Why is this glow, these filaments, why are they not steady? Why are they moving around? I will answer that one. That's because of convection that we will study on this channel in the concepts of atmospheric sciences. You see, when the current is conducted through this noble gas, ionized noble gas, well, it heats up the gas and you get convective currents moving up and down. And these convective currents alter the path of these electrical filaments, and you get this random random discharge of the gas. Well, this was enough of discussion of this beautiful plasma ball. Now let's start with even more beautiful mathematical derivations. Consider a system which can be gas, liquid or solid, containing charged particles which are free to move. If we have that system, and let's say this is x direction in that system, and we apply electric field in that direction, then charged particles will react to that field and move. So let us say that perhaps this is a unit area, A equals 1, and this unit area, as you can see, is perpendicular to my x direction. And as I just said, if we apply a small and uniform electric field in the x direction, then charges that might be somewhere here will react to that electric field. If, let's say, electric field Ex is in this direction, if the charges are positive, they will move along the lines of electric field. If these charges Q are negative, they will move, let's say this is negative charge, it will move against the electric field Ex. So this is how we can conceptually define electric current. Let's call it Jx. And Jx will be the mean electric charge crossing this unit area per unit time in the x direction. Now we can see from this definition that the more particles crosses this unit area in unit time, the stronger the current. And by more particles, what do we mean? Well, there are two options. Either there is literally more particles, larger number of particles crossing this area, or there is indeed perhaps the same number of particles as I plotted here, but they are moving faster through this area A. Either of these two will result in the increased intensity of our current in the x direction. There is a relationship that connects this current with this electric field, and that relationship is that Jx is equal sigma L times Ex, and this is great and powerful Ohm's law. Perhaps it is not in the form you are used to when it comes to Ohm's law, but it is Ohm's law. This sigma L is called electrical conductivity. This, as I said at the beginning, works for either gases, liquids, or solids. But in the case of gases, we can actually find closed form solution for this sigma L as a function of some fundamental properties of an ideal gas. And that is what we are going to do right now. We will consider an ideal gas of particles with mass m and charge q. The unit of charge in SI system is coulomb, which is written, if you want, as COULOMBS, coulombs. As a reference, electric charge of an electron is 1.60217663 times 10 to power negative 19 coulombs. In the case of an ideal gas, these charged particles indeed do not have to be electrons, and most often they are not electrons, they are positive or negative ions. Ion is an atom or molecule that has net positive or negative charge. How could that happen? Well, if an atom or a molecule gains an electron, let's say, then it gets net negative charged, or if it loses one or more electrons, then it acquires net positive charge, and we call these ions. Now let us look into a case where we have a lot of neutral molecules or atoms in an ideal gas, and I will denote them with these black dots. In these neutral molecules or atoms, we also have ions or electrons, whichever one you want to imagine. Let's say these, whatever color this is, would be charged particles. And further, let us assume this is my x direction. Before we turn on this electric field, we need to realize that these charged particles are bouncing off these neutral particles or other charged particles in a random direction, and overall there is a temperature equilibrium in this gas. From one of my previous videos, we know, for example, that there is an average time that these particles will travel before colliding with another particle, and we called that average time tau. As I said, I have entire video where I expressed tau in terms of other fundamental properties of the gas. Now, let us say we apply uniform and somewhat weak electric field in the x direction, like so. So that will be Ex. This will give rise to a mean component of velocity of these charged particles in the x direction. Now, if charged particles are negatively charged, they will move against electric field. If these charged particles are positively charged, they will move in the direction of electric field. So let's assume they are positively charged. That would mean they will move in this direction, along the electric field lines. Let us further define small n to be number of charged particles per unit volume. As always, I wrote it probably a million times. How do you get n? Well, you get it as capital N over V, where capital N is the total number of charged particles in volume V. So that means if all this thing is enclosed in some box, let's say, and this box has some volume, 57 cubic meters, then you count all charged particles in these 57 cubic meters, and you do this division, and you will get number of charged particles per unit volume, which we are interested in. Now, if we go back to this figure, this is my x-axis, and let's say here I put this unit area A. So area of this surface is 1. The question is, how many charged particles will cross this unit area in unit time? Well, to find that, we will use the similar principle that we used in my previous videos when we discussed effusion, when we discussed viscosity, and when we discussed heat transfer in a gas. I will define some critical volume like so, and this critical volume contains charged particles that will cross this unit area A in unit time. So let's say Vc is critical volume, and that volume is, as you can see, this length, which I will call x critical. So it will be x critical times this area A, but area A is unit area. So this becomes 1, let's keep it so you know that this is unit area, 1 times xc, this distance. But I can express this distance in terms of the mean speed of these charged particles that are crossing this unit area. So that will be 1 times xc is mean speed of charged particles in the x direction times some time interval delta t. But as I just said, I'm interested in unit time interval, so this will also become 1. So we can see that this critical volume is 1 times average Vx. But I started asking myself what is the number of particles in this volume, not the volume itself. Well, that's simple. Number of particles in critical volume is the number of particles in unit volume, which is n, times this volume Vc. So this quantity is the mean number of charged particles crossing a unit area perpendicular to x direction in unit time. Furthermore, since each of these particles is carrying charge q, we have that this electric current that I define above is therefore equal, well, Q times NC. And that will further be equal Q times N times average Vx. And as you can see, this is previously defined electric current. What remains to be calculated is this average velocity in the x direction Vx. We shall find Vx using the greatest law ever discovered, and that's the second Newton's law. The second Newton's law says that mass times acceleration is the sum of all forces. I will apply this law in the x direction, so I will get that mass times acceleration in the x direction is the sum of all forces in the x direction. Or I can write that mass times dvx dt is equal, I will assume that the only force is this electric force, electrostatic force, and that force is equal q Ex. Now this is the part where you either have to trust me or you know the expression for electrostatic force. This is one of the first equations that you learn in electrostatics, so I assume many of you know it. But if you do not know it, electrostatic force rather, is equal charge times electric field. Now this is clearly a differential equation that separates variables because we assume that Ex is uniform and constant in time. So this becomes dvx is equal qex divided by m times dt. And now I can integrate this expression. Now at time t equals 0, I will have some velocity Vx0, initial velocity of these charged particles, and then at time t they will establish some velocity Vx. And time t equals 0 represents what? Well, that is the time of the last collision that this charged particle had. Any of these charged particles, of course. So this is very important to understand, that I am referencing time to 0 when particle had its last collision, and then time is passing and particle establishes some value of velocity along the x direction Vx, and it establishes it because of this electric field that is applied over here. Now if we solve these integrals, we will clearly get that Vx is equal Qex divided by m times t and plus Vx0. Here I will apply averaging operator, as I often do in these cases in kinetic theory of gases, and we will get that average Vx, because that's what I'm interested in here, is equal Qex and m are constants, so they are not affected by averaging. Here I have average time and plus average Vx0. Let us look into this average Vx0. What I will say now are very important arguments. We shall assume that after each collision between these charged particles and these neutral particles, the charged particles on average restore to thermal equilibrium. What that means in more layman terms is that when a charged particle, let's say this one, collides with neutral particle, let's say this one, it bounces off in a random direction irrespective of the particle's past history. What I mean by that is the following. Let's say here is my neutral particle, and here is a charged particle that is going to collide with this neutral particle. After the collision, this charged particle on average could continue in any given direction. On average, that's very important. Of course, a single collision, like this collision, perhaps will end up in this bounce of the neutral particle. But if I average this over many collisions, then I will see that the direction of reflection is pretty much random. And that means, averaged over many collisions, this ends up being simply zero. You will kindly remember that we had absolutely same argument when we defined temperature in my video on temperature of an ideal gas. Furthermore, you can see that this average time we already defined as the mean time between two collisions, and as I said, I have entire video on deriving tau using other fundamental properties of the gas. So all these together lead to average Vx being equal Q Ex over m times tau. Let me just go back to this figure and explain something conceptually. And what I want to explain is how do we average? When I say average over many collisions, there are two options we can do it. We can say this charged particle, let's call it particle 1, is going to collide with this neutral particle, and then here it will collide with another neutral particle, and then it will bounce off in this direction, and then over here it will collide with some other neutral particle, and it will bounce off in this direction, and then so on. After every bounce, it has a random initial velocity Vx0, but that initial velocity will be adjusted after certain time by the effects of this electric field. So perhaps it will look like this initially, but then it starts curving in the direction of electric field, like I indicated here, and then it encounters another neutral particle. Perhaps it bounces in this direction, let's say, and then over here it will again be affected by the electric field, like so, and then here it encounters another particle, but after colliding with it, it will continue in this direction. And then again it is affected by the electric field, and you can see how it will propagate in this direction of the x-axis as I indicated here schematically. Another option to look into this is not to follow this particle 1, but to average over some very large space where we have billions and billions and billions of these charged particles colliding with neutral particles, and then at the end of the day that's the same as following one particle that will encounter billions and billions collisions. What I just said statistically is also called ergodic process, by the way, for those of you that love statistics. Now you might say, but what if this is not the case? What if the charged particle kind of remembers its history after the collision with neutral particle? That is possible, of course, and then we would say that there is the persistence of velocity effect, but we will neglect that effect. Persistence of velocity effect indeed occurs in gases that are subjected to this electric field, but we will neglect it. If we neglect it, then a good argument to use is to say that these neutral particles are much, much heavier than the charged particles, and they will result in random direction of the charged particle after colliding with the neutral particle. Okay, going back now to this equation, if I substitute Vx in this equation over here, I will get that Jx is equal Q times n Vx, but Vx is Q Ex divided by m times tau, or it follows that Jx is equal nq squared divided by m times tau times Ex. And this quantity over here is called sigma L, which I introduced here as the electrical conductivity. So you can see that we derived Ohm's law using kinetic theory of gases. You can see therefore from here that Jx is equal sigma Lex, and that's the Ohm's law that we started this video with. Therefore, you can conclude that the beautiful kinetic theory of gases gives us the expression for electrical conductivity in terms of microscopic properties of ideal gas, namely charge of particles, mass of these particles, mean time between two collisions, as well as unit concentration of these particles, of course, per unit volume. Yes, now you became expert on kinetic theory of gases and you know Ohm's law beyond this simple equation J equals sigma E. You know how to express sigma, electrical conductivity of an ideal gas, in terms of fundamental properties of these gases. Later, when I start my playlist on electricity and magnetism and electrical phenomena in the atmosphere, we will dwell in more details into some of these concepts, but for now, I think you have good understanding of how gases can conduct electrical current. You see, Richard Feynman, great Richard Feynman, said if you have a powerful theory in physics, that theory can often give you insights into different fields and theories in physics. And this is the case here. Kinetic theory of gases is very powerful theory. And I believe, this is my opinion, Maxwell, Boltzmann and others, when they were developing this theory, their first thought was not electrical conductivity of a gas. Yet, the theory is so good that when you apply it to electricity, you get better, deeper, more fundamental understanding of electrical conductivity of an ideal gas. Please make sure to share this video with several people. I would appreciate that a lot. Until next video, goodbye.